Hi, hello everyone. Oh, it works great. Thank you for joining, especially in so large numbers. I'm a bit more stressed now than I expected, so you'll have to excuse me. So as mentioned, my name is Armin Reinert. I lead data science team at Empik. And with me is Alicja Jośko, senior data scientist at our team, who led an effort on this project, and not just any project, but the project very close to what Empik DNA is, so obviously books. Because as you probably know, a core of our business is actually selling books. We obviously have other parts of it as well, quite big online presence, also other assortments at our stores, lately increasingly so. But books, it's still something people associate us with, and something that is a large part of what we do and what we sell. And with this image comes also expectations from the clients that when they actually enter our store, they will find there the book they look for, or maybe something interesting for them and they didn't expect to find there. And our project was about that. So basically about putting in the stores the books clients would be looking for. And as simple as it might hear at least to put it into the general formulation, it was not an easy task, because as you may see on the slide, there are some challenges both on the supply, let's say, side and demand. Because we have a lot of titles we can choose from to put into the stores, both novelities and more popular titles, but from older times, some classics and some undiscovered authors, and so on and so on. Roughly through 100,000 at any time, in many different genres, from classics to self-help books or cooking publishers and so on. So the choice from which we have to decide on is quite large, and also our network. So our stores are quite diverse. So we are present in many locations across Poland, from city centers to some more remote, smaller towns. The clientele there is a bit different, and also format of our stores are differ, because we have both quite large formats with 20,000 possible titles to put into, and also some small stores with 8,000 capacity. So order of magnitude less than we can choose from. What does it mean? That we need to be smart about what we put there to actually meet client demand. And if you think about this problem in the beginning, it might actually seem like some pretty basic panel data prediction problem. You have several stores, several titles, books. So let's just predict for each of these books what will be the size at any given store, and put the stores the books with the highest possible prediction. Yeah, like simply as that. So you need to collect historical sales, obviously, how those books actually sold at the sales point. Create some features, create model, create ranking for each store, ship it to the business people and let them figure it out. And it might look so, but some problem, as you imagine, might arise. So first of all, this prediction, I say like pretty basic panel data prediction problem, and to its core, it's true. It's a bit large, over 300 stores, 100K books, already quite a lot of predictions to make. A lot of them with very little information on size, because as you may know or imagine or not, the books in the back catalog, so less popular ones, don't really sell that frequently. But these are standard, let's say, difficulties which any competent data scientist probably can overcome after some experimentations and so on. Of course, some challenges with testing these predictions, but all in all, sounds doable. A bit or more problems may arise when we actually start thinking if this is the prediction, as I described it, which we need. Because, yes, obviously, we can predict how a given book sold at a given store, but maybe this book was never there. Like, we don't put every book everywhere at some point just to test it. Maybe it was there, but it's not there anymore, and so on and so on. A bit more on this topic later. So it might be not that easy to predict the sales of every book for every store. But still, it's interesting prediction exercise. Maybe a bit more difficult to imagine and to solve, but still, like at its core, data science focused. The true problems may arise when we think about this last point, when we just ship the list to the business people and let them figure it out. And they might come to us with few issues, which might actually influence how we'll be thinking about this problem. Because first of all, managing separate lists for every stores might be quite challenging. It's over 300 lists of assortment with different lengths and so on, different requirements, maybe completely different set of examples. Like someone still needs to ship this book there, put it into the shelves and so on and so on. Not that easily doable. Not every product is available at any given time to us. We need to order them from our suppliers. There are some lead times. Sometimes there is no paper, so they cannot print it. Popular problem last years. So this is another thing we need to take into consideration. All of it costs money because we need to ship it to the store, place it on the shelf. It takes operational effort, time from the people working in our supply chain operations, in source operation, and so on and so on. Next, we cannot just randomly place books into the shelves. As you may know, we typically group them by genres, typically have at least one full shelf for any given genre. So we cannot just determine that the elements of statistical learning would sell great, so we should put it there and not put any other informatics or technical books at all. So this is also a problem to consider. I mentioned frequencies, and also some products just have to be in a store. We have some agreements with publishers, we have some PR considerations, or we just want to have some books there, like Szymborska Poetry or Pan Tadeusz. And they may not necessarily sell that well. And as you may notice, all of it concentrates at the very end of this process. So obviously we can prepare predictions and then try to think about the rest, how to make it work. But it would be smarter to actually start with it and start thinking how to put the whole process in the context of these challenges I mentioned.
Yeah, so actually these challenges are what makes our work interesting, and confronted with this, we had to redesign the whole structure of the project. So when you look at the workflow which we actually followed, here the sales prediction model which we put on the first slide is just a small piece in the entire puzzle. So besides the prediction model, we also have segmentation, classification model, and 2 optimizations, so much more. Let's look more in depth into all those elements. So as Armin already said, it introduces a huge operational complexity to manage store assortment on a store level. And it might be a good idea to group stores with similar sales profile together, creating segments. And of course, we achieved it through store segmentation. We used sales data from online, offline, and created groups of stores with similar sales profiles. But Empik opens new stores every year, more and more stores. So for those stores, in new locations, we don't have full information. So for them, we need some separate treatments. And we built another model, classification model, which use the data about the surrounding of stores, source features, and classify those new stores into segments so that we can also manage assortment in these new stores in the day of the store opening. These two created segments, and they fit into the sales prediction model, which is in the core still, but needed some tweaks as well. So we needed to cover for the hidden demand already mentioned. So not every book is in every store. We had to account for that. And besides, and we will talk about in more depth. That's why I'm skipping it later in the on the slides. Besides that, we also had to make sure, of course, that we have the right forecasts. So we adjusted loss function, evaluation metrics to the distribution of our data, but that's a separate topic. We won't be focusing on the quality of the prediction itself. From sales prediction model, we can generate a ranking of products starting from those that are predicted to be the best selling, ending with those worst selling, and based on that we could determine assortment in our stores. But this doesn't include the cost we mentioned, so there's another part where we optimize our rankings for costs. And when you look at the other trajectory on the right-hand side, you can see another optimization we did, where we took care of the shelves arrangement inside our stores. About all those two optimizations, we'll talk on the next slide slides in more depth. And although those elements, they meet at last in the operationalization phase, and if this operationalization phase is proceeded with all those steps, should go, and for us did go pretty smoothly.
Yeah, so going a bit in detail to some of these points I mentioned, the hidden demand, let's say so, problem. Although there's some definitions here for demand, it shouldn't be hidden. Like demand is what people expect to get, but your sales can be actually censored. So if we think about it, there are obviously multiple factors that can influence our sales: prices, availability, the general quality of book, and so on and so on. And they all need to be taken into consideration. But there is one defining factor that will always result in zero sales, and that is lack of book in a store. And it's quite a common problem. It either might be there, but being removed. It might never actually appear in the store, at least in the foreseeable past. It might sold out for a moment and then return. So the availability might also not be like 0, 1 variable, binary one. It might be there for Monday and to Friday and then sold out for the weekend. And all of this might result in reduced or zero sales, which our model would probably predict, but this is not the prediction we are interested in, because we want to know how well the book will sell if we actually put it into the store and it will stay there. Because that's what we are deciding upon, yeah? If we should put a book in a store. And we are in a fairly comfortable position in a sense that, okay, we might not see all of the books in all of the stores, maybe not either in none of the stores, but we have our online channel, which more or less has the book available. If the book is not there, we probably cannot really put it into the store either way, so it doesn't matter. And we have many stores, so some books could be in some of them, some could not be in there, but we have some mix which we can inference from. And also, like, one additional important factor to remember here is that the zero sales might be also a result from books just not selling. Yeah, so it's not that we have zero, so book was not there. It might just not be that particularly good book. And when we think a bit about dealing with this problem, we actually want our model, too much about books, our model to achieve 3 goals. So first of all, it needs to be able to predict sales well given normal conditions. Yeah, like you still need pretty good, solid, predictive model, which given all possibly relevant factors like seasonality, past sales, price, some product information, web traffic, mailings, etc., promotions, will be able to tell you how the book will sell create some baseline, so to say. But on top of that, the model should do two additional things. So first of all, it should actually well capture the effect of availability of the book in the store or segment or network in general. So more of a econometrical thinking here, when we not only focus on prediction, but we also actually want to capture the effect of putting book there. Of course, it's easy to do one way. Just if we don't place the book, the sales will be 0, but not that easy to capture another way around. And first of all, we want the model to be able to learn from other sources. So if the book sold well in other stores, in a segment, maybe it will sell well in this another particular store in a segment. If the book sold well online, but was never actually present in a store, maybe it will actually sell online, also sell well also in a store. So two these additional things, the effect of availability and the effect of other factors. Accounting for this availability part can be done first of all, but well defining and well maintaining, let's say so, the availability variable or variables, because we should probably consider at least few of them here, and actually measuring if the effect of the variable is what we expect it should be. So it should be considered in the validation as well. But also we need to remember that it's not like any variable. First of all, the variable will be influencing by ourselves. So it might behave differently in our training or even in test, and differently in scoring on production. Because if we test performance of our model or even train, then the availability factor or variable should probably just take values as it was in reality, just to test if our model is able to capture this effect well and translate it into the proper size prediction. But if we do scoring, we should actually assume the whole availability in all cases, because that's what we want to test. So how well we sell, conditioned on availability in the store. So important fact to remember. This consideration actually might also go further to other variables, maybe promotions as well, if we want to actually have effect of promotion in the sales or no. And maybe some others, but that's not that important right now. We need to also remember, while creating features, that this is a factor influencing our feature creation as well. If you want to aggregate how well on average the book sold in specific segment, we cannot treat any 0 the same. Because if the book didn't sold because it was unavailable, it shouldn't be considered in the average sales. Like it couldn't sell well or not. It couldn't influence the average sales in positive or negative way. We just don't know. But if it was there and it didn't sold, yeah, that's an information we should probably average with it, and it extends to other features creation as well. But I think you get a gist. So this is the thing about the availability factor. Moving to this learning from other sources, so from online sales or other store sales, we of course should and have put proper features into our model. So online sales, maybe sales from the capture area of a store, sales from similar stores, and so on and so on. But we may still find ourselves lacking a bit of the information, especially for less frequently sold books, on how such books may actually behave if there was no sales in this particular store or in similar store and so on. So what we discover, it might be beneficial to actually ingest some artificially created lacks of availability, let's say, in the sources we can learn from. So either from the history into a given store or in other stores as well. In theory, you can also pretend that there was no sales online, but then the model doesn't really have anything to learn from. So it doesn't make the point. And as already mentioned, these manipulations should be also treated with some consideration by validating our model both in a sense of if our effect was captured well, but also if it still is able to predict its predictive part of target.
So we are coming back to our workflow. So we are now in the phase where we have the prediction. And what we could do, we could actually build a ranking starting from the best selling, ending at the worst selling, and then we can get store capacities. So how many products a store can fit, and we can start fitting from the top of the list and where the store capacity is finished. However, there are two facts which you should know about the market we operate in. So first one is that we have store assortment modification costs. So it costs us money actually to replace a book with another one. We have ordering costs, we have delivery costs, we have packaging costs, etc., returns costs. Another fact is it's a market with infrequent sales, especially books. So let's be honest, you don't buy a book every single day or every single week, at least not everyone. And when we combine those two, we can find ourselves in a situation where in a big Empik store like in Arcadia, we are exchanging a book which is predicted to be sold at almost zero quantity with another one. Like we are in the middle of winter and we are switching atlas of butterflies to atlas of mushrooms. So it doesn't make sense because none of them will be sold, but our store is pretty big. So it doesn't make sense. That's why we have to consider costs, put costs into the whole picture. So we'll now dig deeper into how we did this. So from thinking about revenue from sales, we switched to thinking about profit from sales. Our initial ranking, as I mentioned, is based on the predicted sales for around 1 month. You can create a myriad of variations of this initial ranking by reshuffling products. And for each variation of this ranking, you can calculate the total profit, which would be the difference between revenue from sales and costs. And from all those variations, we would like to choose the one that is maximizing profit. It sounds easy when we introduce it like this, and to understand it even more, let's look at the dummy store example. So it's a store with a single category, because we have to do it on a category level. We have capacities defined at a category level, so for fantasy, crime, separately. So this store can fit up to 5 products in a certain category, and based on the initial ranking, we would have to stock product A, B, C, D, and E. And it would mean that since product E is not yet in stock, we would have to incur costs of delivery of this product. And as it's going to replace product F, we would have to also take on the return costs of product F. So it's worth asking the question if it's worth it, if the cost is compensated by the increment of sales. Maybe there is not such a big difference. And if the answer is no, then we should probably switch places of those products. But we can't do it iteratively, as showcased here, because we have hundreds of thousands of products, and the lists are created on a store level, on a segment level, not on a store level. That's why we needed some systematic solution. And how did we do this? So we simplified this problem into a mixed integer linear optimization problem. We took the data. First, we took the store layouts, so it showed us how many shelves we have for each product category in each store. We took stock. It showed us what's already in store, and we wouldn't have to cover for any shipping in or shipping out costs. Thirdly, when it all comes together, because we are taking the predictions from our model, but here we have to disaggregate it into the store level model. And lastly, our costs of delivery and return, including all of those that I mentioned before. We transform this data, we create a master table, and we are at a point where we want to perform optimization. How do we define the optimization problem? The problem is that we have a dissonance between the store-level data and the results that we want to have on a segment level. So rankings are on a segment level. We address this with a small tweak. So from thinking about on which place a product in the ranking should land, we switched to thinking about how many stores a product should be introduced. And in such definition of the problem, the decision variables, the constraints became very easy. Decision variable would be if a certain product should be in a given bucket, where a bucket is a set of neighboring rank places a product can land on. It means that if a product lands in the first bucket, it would be stocked in every single store in a segment. If it's in the last bucket, it means that it won't be stocked in any of the stores. And the bigger the store, the more buckets, of course, it can fit. And the constraints, as simple as that, a single product can land only in one bucket, and the number of products in the bucket is equal to the bucket width. While keeping the objective function, maximization of profit as a difference between revenue and costs. We are back again on our workflow slide. So we'll now dig deeper into the other optimization which we did. So is there anyone who has never been to an Empik store? I assume you all know that we organize our books into shelves of certain categories, and then similar categories are put next to each other. So it provides a nice shopping experience because it helps our clients navigate the stores. But it's another complexity which we had to face. And again, we solved it with an optimization module. So actually, it was the solution was pretty similar because again we used mixed integer programming, so I wouldn't get into too much detail about it. But what we used here was the prediction of our model. So we had sales predictions. We batched products starting from the top of the ranking into shelves, and then we wanted to find the optimal set of shelves for each store. So we had separate problems for every single store. We also had some constraints, mostly coming from business. So like minimal or maximal number of shelves for each category dictated by availabilities, PR issues, stuff like that. And then allowed mixes of categories, like some categories can mix together, the others can't. And the operationalization, we have a team creating store layouts, and this is happening.
Yeah, so all in all, you've seen a snapshot of the complexity that went into this problem. Few of these boxes here, and not even explored that in depth. And I think like what was for us particularly interesting and great about this problem, that it actually evolved from fairly boring panel prediction issue to this beautiful, complex, multi-factor challenge based on this, you may say, boring or frustrating business requirements. Yeah, like certainly I often think about all these business constraints as issues a bit limiting what we can do. But as we can see, that can actually add a lot of complexity and interest to a project. What's also important, it also did work quite well. On this test set of stores, we've managed to achieve anywhere between 5 to 15 percentage point of increase in sales dynamics It is a lot. So we are also happy about that. That it was not only interesting to do, but also resulted in such significant business outcome. To end, we'd like to thank the whole Empik team involved in the project. So, of course, our data science team members, Gabi, Adam, Szymon, Kaja, and all others, but also the people on the business side from project management, maybe Michał and Ola, but also all other teams from our supply chain, commerce, merchandising, IT, store operations, and so on, and so on. And I believe we still have some time for questions, so we gladly take one.
Yeah, now to questions.
I think there was someone first.
So thanks a lot. It was super useful presentation, and I really like that. Just wanted to ask about the general problem that we often face doing assortment optimization, which is product cannibalization. So I guess that's not such a big challenge as in, let's say, grocery industry, but I imagine you can still have, like, for example, case where people are buying, let's say, a dictionary, which is still a book, and like the person can choose between a couple of those, or looking for specific, for maybe not specific book, but something that falls into category of, I don't know, crime or something, stories. And then I'm thinking, do you have any analytical approach to model the cannibalization of the products?
So we did consider it, but not that in-depth analytically, to be honest. We have some categories, books, and so on identified, like possible cannibalization ones. As you mentioned, it's not that big of a problem for us. I think kolorowanki, coloring books were the most issue-generating ones. And this is then driven by company policy, like which one should we choose. In main categories and in our main money makers, let's say, so we don't face that much of a problem in this area, so we didn't put that much time into it.
Hey, one more question here. You mentioned that it was very important for your model to have a proper way of addressing the availability variables. Could you share some tips on what's the best way to include this information in sales prediction model?
Mm-hmm. Yeah, so it will be a bit of a case dependent. In a sense, few issues from our side, maybe to organize it. First of all, you need to find the right way to actually address if someone was available to a client or not. Because many times in the data you'll see information that something was in store but might be on a shelf, maybe on the extra exposed shelf, or just in the warehouse, but from the store. So it's something to consider. It is important to consider like when and for how long it was available. And it also depends on the structure of the data, because sometimes you have stock data and sales data which are updated not that frequently. And it might be that something has been sold in the morning, but you will see lack of the book only in the evening, or another morning, and so on. And it might be important, especially that many of our books have only one face. So we need to try to track it as well as delivery times and so on and so on. I think that it's very operationally driven. So I'm not sure I can give all the answers, but I hope I at least give a taste like where the problems might be.
Thank you for the interesting talk. How do you deal with books and the new books that you don't have any historical data on?
Mm-hmm. That's a great question, and a bit of a different project, I say. because dealing with novelities, determining what to put where in which amount, it's partially driven by, it's like fully driven by other process. So we have actually set aside a space for novelities in this approach. And we look at the books only at the moment when we have some information about its size, either online or in store and so on. And then, of course, it can appear in larger amount or in smaller amount. And the process of novelities itself will be driven both by models which try to predict how new book will do, and commercial agreements with publishers.
So how quickly, if at all, can this approach react to like random occurrence from outside of the your books, or so, like Tokarczuk winning a Nobel Prize or book trending on TikTok, stuff like that?
Mm-hmm. So it is binded to the assortment replenishment process. So for us is like Tom Kultury, relevance driven, which is every month or every 2 weeks, depending on the period. So this is like operational restriction, not model restriction, because we do not replace this assortment every day or every week because of the cost mentioned. This is quite of an operation to move in new books, even with this restriction that Ala described.
Yeah, if you have any other questions, please discuss them with the speakers. They'll be surely happy to help you. And don't forget to rate the presentations by scanning the QR codes. And you can also do this after when the recordings are ready. Yeah, thank you guys once more.